Hello everyone. Welcome to lecture 5 of module 5, which is on combinational circuit design. So far, we have been looking at the static CMOS design. This lecture onwards, we will be looking at the alternate logic designs, when are they needed and why are they useful. So disclaimers remain the same. So first, let us discuss what is the need for alternate designs when we already have a static CMOS design which is performing well, right? It is also, there's this ease of implementation of them in the automated tools that we have right now. So why do we need these alternate designs? So let me just briefly discuss some of the properties of static CMOS design. So you saw that you achieve a full logic swing. Full logic swing definitely means that you have a large noise margin. Furthermore, it was a ratioless logic. That is, the logic levels, the nominal logic levels, that is VOH and VOL, they do not depend upon the sizing of the PMOS and NMOS. The delays do depend on that, but the static values, VOH and VOL, no matter how, no matter what you size your PMOS or NMOS, it will drain the output capacitance to ground for NMOS and it will charge it to VDD if you talk about PMOS. So that thing is not dependent upon the sizing value, right? So it's called a ratioless logic. Also, there's a small static dissipation. I mean, when they were developed, they claimed that there was no static dissipation because the subthreshold currents were pretty low. But nowadays, subthreshold current is high, and we say that the static dissipation is kind of appreciable, right? So I would put it like there's a small static dissipation. For modern technologies, that doesn't that's not true. The static participation is also large, but for the conventional ones, I mean, when they were developed, we can definitely say that in those times, the static participation was pretty small. Now, what are the disadvantages? I mean, so far I have been talking about the advantages. What are the disadvantages? So for N input design, we have to use 2N MOSFETs. So if we are using 2N MOSFETs, first, there's a large area. And you'll find out that this PUN is redundant. We can design our logic by using either the PDN or the PUN. So even if we have one of those, we can easily realize the logic function, right? PUN and PDN were mutually exclusive in CMOS, like static CMOS design. And that was just to achieve these these advantages. Even if we don't have a PUN or a PDN, we can realize the logic with the other part of it, right? Since there are 2N MOSFETs for inputs, there's a large area. And also, since there are 2N MOSFETs, there's a large load capacitance as well, right? Because it's actually sum of internal load capacitances, like the internal capacitance plus the exterior capacitance, right? So if you have a large number of MOSFETs connected to the load terminal, then you have large load capacitance as well, right? And C contribution is large. Also, the internal capacitance would be large. I mean, the capacitance at the internal nodes. If these two are large, then definitely delay will increase, and also dynamic power dissipation, that will increase. Because when calculating dynamic power dissipation, you have to look at the power dissipation by internal loads as well, right? So input capacitance is also 2N times Cg. Why input capacitance is important? We looked at the method of logical effort, right? So there, this logical effort G, that was dependent upon the input capacitance, right? So if the input capacitance is large, then your logical effort, that is also large. So the delay would be, the slope would be larger. With effective fan out, your delay will increase with a large rate. That is also true for static CMOS gates. However, things like large noise margin, full logic swing, these things make it promising. And also it's easy to make, these static CMOS gate using automated tools. I mean, library design is easy that way. So that is also one of the reasons why we have been moving ahead with static CMOS design even now. However, if this area and speed are most important constraints. For instance, we want to talk about IoT sensors, which will be deployed in some remote area. So there, what happens is, when you are in a remote location, then first of all, since you're talking about sensors, so sensors are typically pretty small, right? So the area has to be pretty small. So in those areas, in those kind of conditions, or when those are the important constraints, static CMOS design is something that can be overlooked, and we can go for some other designs, which I'll be talking now. So whenever area and speed are most important constraints, we don't care about noise margin, full swing, and so on, then we can go ahead with what is known as ratioed logic design. Why ratioed and so on, I'll discuss that later. But first, let us go ahead and see a style of logic design which is called pseudo-NMOS or pseudo-logic design or pseudo-NMOS logic design. So what exactly is this? So in pseudo-NMOS logic design, which is a ratioed logic, what we do is replace the pull-up network with a single unconditional load. Now, in static CMOS, what used to happen was PDN and PUN were conditional, right? So if PDN is on, PUN will be off, and the output will be drained to the ground. If PUN is on, then the output will be charged to VDD. Load will be charged to VDD. So there the PUN was conditional. It was depending upon the input, right? But here, in the case of pseudo-NMOS logic or a ratioed logic design, what we do is we replace this pull-up network with a single unconditional load that is continuous, like that is pulling up the output node continuously. I mean, it's not like, it is pulled up only when the input wants it to be pulled up. No. Here, the unconditional load is continuously pulling up the output node towards ground. However, the advantage that you get here is it reduces your MOSFET count by n-1. So in static CMOS design, you had 2n MOSFETs, n for PDN, n for PUN. Here you have n for PDN and only one transistor for pull-up network because that is an unconditional load. So here the MOSFET count is n+1 as opposed to 2n. But since this is always turned on, so if the input is also, if the set of input is such that the PDN turns on, then since the unconditional load is also turned on and PDN is also turned on, it will introduce a static dissipation. So this is how a pseudo-NMOS logic design looks like. So you kind of replace this overall PUN with a PMOSFET and then you ground its gate. What it means is its VSG is always, its VSG is always equals to VDD, so this is always on. So regardless of whether PDN is on or off, this output is always like this tries to pull this output towards VDD, right? So as I discussed, PUN in static CMOS gave a conditional path between VDD and load, but here this unconditional load, it is giving a path between VDD and output always, regardless of PDN is on or off, right? Now, what are the options? I mean, what are the options for this unconditional load? One is this PMOS with a grounded gate. Remember the discussion on inverters? So we also have this depletion mode and MOSFET with grounded gate as one option, right? That is what we use for inverter design. Here also we can use it. And the other option that we have is we can also replace this PDN with unconditional gate biased NMOS and use PUN for realizing the logic. This is also possible. And in this case, it's called pseudo PMOSFET design. So here what we do is we replace PDN with NMOS and its gate is connected to V supply. Actually, it should be V supply plus VTN, right? Because no, it's fine. I mean, here it can be V supply also because we are not going to pass logic 1 here, right? So here V supply works fine, right? So here what is the difference? I mean, you replace PDN with this gate biased NMOSFET and everything else remains same, right? So here this will try to pull this output towards ground, irrespective of whether PUN is on or off. Now, what is the disadvantage of this? Since it's trying to pull this up all the time and PDN will try to discharge it, so there is a tug of war going on between this unconditional load and the PDN. And that leads to VOL, which is not exactly ground. And that tug of war, I'll discuss that in the next slide. And we have to, size this unconditional load properly so that, VOL is small or your logic swing is large. So that is why it is called a ratioed design. Okay, so let me go to the next slide. So what is VOH here? VOH is simply VDD, right? Why is VOH VDD? So let us assume that, the pull down network transistors, all of them have a VOL which is less than VTH of them, right? If the VOL is less than VTH, there is threshold voltage of these MOSFETs. You can assume that PDN is turned off when you apply Vin equals to VOL. And in that case, the output will be VDD, right? Because this unconditional load will charge the CL to VDD every time. However, the inherent assumption is that VOL is less than VTN. And obviously, there is no subthreshold leakage because if subthreshold leakage is there, then also there is some change in the logic levels, nominal logic levels. However, as I discussed earlier, VOL is not ground. Why VOL is not ground? Because even when PDN is on, even if the PDN is on, your unconditional load is trying to pull that node towards the VDD. So there's a tug of war going on between PDN and the PMOS, right? So if VOL is not ground, what it leads to? It leads to a reduced noise margin. And also since unconditional load as well as the PDN is turned on, so there's a path between VDD to ground. So static power dissipation will also be good. Why it is called ratioed logic? Because we have to size the unconditional load depending upon the constraints of noise margin, delay, or power. Why delay and power? Let us also see that. So in static CMOS, it was non-ratioed logic because VOH and VOL is size independent. No matter what you size PMOS and NMOS, your output in static condition is always going to be VOL equals to ground and VOH equals to VDD. However, here, depending upon the size of relative sizing of this unconditional load and the pull down network, your VOL is decided. Now, how do you find VOL here? So you just equate the currents for load and the pull down network while assuming V equals to VOH equals to VDD for the PDN, right? Once you do that, let's say you have a circuit like this, right? So here what is F? F is simply A dot B dot C dot D whole bar, right? Now, let's say that in worst case, only one of them is turned on. So how can you find the VOL? So VOH here is VDD. Let's say when VOL is less than VTN, so all of these transistors would be off. And we can say that this will charge the CL to VDD. So VOH is equals to VDD, right? Now, how do we find the VOL here? Let's say only one of these is turned on in the worst case. And in that case, what happens? Since VOL, output is VOL, input is VOH, that is VDD. Since output is VOL and we assume that it is less than VTH, so the drain voltage VDS of this NMOS is smaller as compared to VGS, because VGS is what? VGS is VDD minus 0. So VGS is VDD minus VTH is actually greater than VOL, right? So in that condition, this NMOSFET is in the linear regime. We use the expression for linear regime. And what about this P MOSFET? Since this is pretty small, its VSD is larger as compared to VSD minus VT, right? So this is in saturation region. So your N MOSFET is in the linear mode, P MOSFET is in the saturation mode. It may even be velocity saturated, depending upon the conditions, the critical electric fields, and so on. So you use the expression for that. And then when you equate it, you find the value of VOL, right? Now you can see here that VOL actually depends upon VT, VDD, and also the ratio between KP and KM, right? So from this expression, what you see that if you want to minimize VOL, since it's 1 minus something, you will have to size P MOSFET smaller than N MOSFET because you want this term to be as large as possible. And for that, KP by KN should be very small. Right? It is evident even from here, physically also it's evident. If your P MOSFET is showing a small pull-up power, then as compared to the pull-down power of this N MOSFET, then only you can say that this ground will be pulled closer to this node F will be pulled closer to the ground if the pulling strength of A is larger than the pulling strength of this unconditional load. And how do we make the pulling strength or driving strength higher? By increasing the width of this as compared to this. So the width of the P MOSFET, unconditional P MOSFET here, should be smaller as compared to the N MOSFET. However, there is a trade-off, right? What is the trade-off? So trade-off is when you are charging this like TPLH of this circuit depends upon the resistance of this, right? When you are sizing it smaller, its resistance reduces. So this increases your TPLH, right? Now, about all that discussion, what's the gist of it? So the gist of it is that, static power dissipation is something that limits the utility of this design. However, it's still finding use in some designs where, area is most important. For instance, when you're going for large spanning circuits, when your area is most important and you can use it. Now, is there a way we can introduce, we can reduce the VOL to ground? We can realize full logic swing. So people came up with this circuit in which what they did was they put a feedback to your unconditional load. So here it is not unconditional. Here you have put a feedback. Now what happens here? Let's say that this output node is DOL. Let's say that the PDN is true, and here we have been able to pull this to VOL, which is greater than ground, right? Now since this is greater than ground, but it's still less than VM of this inverter. So if this voltage is less than VM of this inverter, then what it will do? It will convert it to logic 1. So if logic 1 is applied to this load, then what happens? This turns off. So if this turns off, then it's not able to pull this node further towards VDD. So this node will further discharge to the ground. But in that case, once it is discharged to the ground, can we charge it to VDD again? No, that's an issue. So this design was discarded. Although it was able to realize this full logic swing, but the moment it was like the moment this node discharges to ground, whether we can charge it again using the same circuit? No, we'll have to use another circuit to charge it. So that kind of reduces its utility, or I would say that was a disadvantage. But the advantage in terms of area, let me show you that. So a simple 2-input NOR can be realized with just 3 transistors, just 3 MOSFETs, right? And there we used 8. So look at the simplicity of this design. So that is the reason why even area is most important. We use this kind of logic design. Now we need to we need to have a full logic swing, rail to rail swing, and so on. So for that there was another family of logic design which was based on pseudo NMOS design as well, pseudo NMOS design itself, but that was known as differential logic gate design. So this differential logic gate design, what it does is it basically eliminates the static current, which was a problem for pseudo NMOS design, and it also enables rail to rail swing. Here, what exactly happens in a differential logic design is that each input is provided in both true and complementary format, and the outputs are also obtained in both true and complementary format. What it uses is, it uses a positive feedback similar to the one that I discussed earlier, but there was some problem with that. But here in differential logic gate design, this positive feedback, it is used to switch off the unconditional load and eliminate P static. Even there it was the case, but that wasn't successful. This differential, if you implement the same circuit in the differential form, it makes it work. So that is why we are discussing this. So there's this class of logic design which is known as differential cascode voltage switch logic, which is DC-VSL. It's very important because it comes out, or it emerged out of this pseudo NMOS design itself, but it doesn't show you static current and it enables rail to rail swing. So here this DC-VSL is only NMOS logic. There was no PMOS used here, right? And here what exactly how you can design a DC-VSL is, so here you will have 2 different pull-down networks. So you will have 2 mutually exclusive pull-down networks, PDN1 and PDN2. They are dual of each other. So only one is on at a time. So one is off when the other conducts. So both pull-down networks are kind of designed mutually exclusive. They are dual of each other, such that only one of them conducts and the other one remains off. The advantage of DC-VSL is that it can realize both output and its inverse. So if both output and its inverse is available, you definitely reduce the gate count by half, right? Because you will require another gate to realize its inverse, or you will at least require an inverter to produce that, right? So the gate count is actually reduced. So this is how your DC-VSL logic looks like. So only NMOS logic, I mean, that means that the pull-down network is only NMOS. In a pull-up, it's PMOS as well. Don't confuse with that, sorry. Okay, so here we have 2 pull-down networks. One is Boolean function F, PDN1, which realizes Boolean function F, and there is PDN2, sorry, it should be PDN2, which realizes Boolean function G. And F and G are complement of each other, and therefore, these 2 pull-down networks are dual of each other. And here we realize output, and here we realize output bar. Let us look at how it works and how it provides you rail-to-rail swing and so on. But first, let us also discuss about its advantages. So first, I discussed that it reduces the gate count significantly. There is no need for inverters, right? And also, when you are using inverters to produce inverse of any output, then there's a delay which is introduced by that inverter. So there is this time synchronization issue. There is a glitch, So if you want the output and its inverse to reach a place at the same time, it cannot be possible because the inverter will definitely introduce a delay, right? So it resolves that time synchronization issue as well and reduces the glitch which was present because of the inverter delay, right? Now let us understand this circuit. So what happens is, if F is true, what happens? This output is discharged to the ground, or its output starts to discharge to the ground, right? Or this PDN1 or F kind of pulls this to ground, right? However, if you look at this output bar, initially it is floating, right? Why it is floating? Because neither output is immediately grounded, nor output, nor this G is on, right? So this node is not connected to VDD or ground because output initially has just started to go to ground. It is not ground yet. So this is not on, right? Now, this output bar is floating and this has just started being pulled up towards the ground, right? Now what happens, the moment this PDN1, that is this F, pulls this output node below VDD minus mod of VTP, that is, the moment the swing across this output goes below VTP, I mean, VTP voltage is reduced. I mean, from VDD, the moment the voltage reduces to VDD minus mod of VTP, this transistor turns on, right? So the moment this PDN1 pulls this output to VDD minus VTP, this transistor turns on, this MOSFET turns on, and as a result, what happens? This output bar is charged to VDD. So the output bar, if that is charged to VDD, it is connected to this pull-up network here, right? So what happens? This pull-up network discharges, or this pull-up network is turned off. So this will be charged to ground, and this will be charged to VDD, right? And you will realize full swing. So output bar is pulled to VDD here. The moment this voltage reaches VDD minus mod of VTP, and at the same time, F will kind of discharge this output way to the ground because this is turned off at that moment. When the output bar goes to VDD, this is turned off. However, during this transition, there would be short circuit currents flowing through this network, and that leads to short circuit current dissipation, power dissipation. And it is also possible to share MOSFETs among the PDNs. So it's not like, the number of MOSFETs required here is 2n because of the fact that you can share MOSFETs among the PDN. So you get a rail-to-rail swing. However, the design is still ratioed. Why ratioed? Because you have to obtain a voltage of VDD minus mod of VTP here by appropriately sizing this MOSFET and this MOSFET, right? So this is one of the sizing constraints on this. I'll discuss this in, or maybe I'll give it in the exam or in the assignment. How do you size DCVSL? That is very important. Think about it once. Also, since you have output and output bar both, therefore there will be two capacitances. So dynamic power dissipation will be larger. Area is also large because still now you don't have n plus 1 MOSFETs itself, you have more than that. Also, one factor that I'll be introducing now, since you have output and output bar here, the number of wires to be routed in your logic is pretty large. And that is something which limits its use. If the number of outputs, if the output and output bar is also there for all the gates, then they have to be routed because they are all connected, right? So that routing becomes very complex, and that is something which limits the use. Although it is showing you all these advantages of time synchronization, delay is also time synchronization is also resolved, so on. But this thing, I mean, the number of wires to be routed, that is doubled, and that kind of limits its use. So we should be very careful. See, whenever we analyze any new logic family, you should be very rational. You should think about these issues: area, dynamic power, number of load capacitances that is increasing or decreasing. Then also this, the number of outputs or inputs, they are increasing significantly, or control signals, not inputs. Inputs is not in your hand usually. But if your number of control signals or clock signals or the number of outputs, they are increasing, output and output bar is there, for instance, then you definitely know that the number of wires to be routed in order to connect them on a chip, that will kind of increase. And that makes the life of designer very complicated. Right? So now we shall also discuss another logic family, which is known as the pass transistor logic. This is also a very interesting kind of logic because this comes out of common sense. So far in all these logic designs, we were kind of using these signals, input signals, we are applying them as a gate terminal of the MOSFETs. So someone came up with this idea that why restrict application of inputs to the gate terminal only? Why should gate terminal have all the fun? Let us apply inputs on the same source and drain terminal as well. So if you start doing that, if you apply the inputs on source drain terminals apart from the gate terminal, then you see that the number of MOSFET reduces for any implementation. And if the number of MOSFETs is reducing, it not only reduces the area, it also reduces the capacitance, right? And the best part about pass transistor logic is it has got a modular design. That is, all gates designed using pass transistor look the same. So if all the gates are looking same, then its layout will be almost same. And creating a library for it so that it can be used for design automation would be easy, similar to the static CMOS design. So this is one more advantage of pass transistor logic. Also, it reduces the area and load capacitance because the number of MOSFETs has been reduced. So how we can realize, let's say we want to realize AND gate using a pass transistor logic. So here you see that we applied D input to the gate and we applied A input to the drain of it. I mean, depending upon the value of A as compared to F, it can be source or drain. Because for a MOSFET, the terminals are interchangeable. Source and drain are interchangeable. Whichever terminal is at a higher potential, that is drain. Whichever is at a lower potential, that is a source. So here, F node is true. I mean, only when A is equals to B equals to 1, you will get F is equals to 1. For all the other cases, F will be floating. It won't be 0. That's one thing, right? Because if A is equals to 0, B equals to 1, you will get a 0. But if A is equals to 0, if A equals to 1, B equals to 0, then this is floating. Yeah. So that is the point. I mean, F is equals to, when A and B are equal to 1, F is equals to 1. When B is equals to 1, A is equals to 0, F is equals to 0. So for those two cases, your F is connected to, either VDD or ground. It's a low impedance node. But when B is equals to 0, F turns into floating node, high impedance node. So what should we do there? We should simply modify the design. How or why? Because the output should not be floating or high in the logic circuits, right? It should not be at high impedance. Output should always be pulled to a valid logic state, either 1 or 0. So how can we modify this design? We can modify this design by adding this another pass transistor. And if we apply B bar here, so when B is equals to 0, this B bar actually conducts and this 0 is mirrored to this F, right? So this circuit, this two transistor circuit represents A dot B. We have been able to realize this AND gate using only 2 MOSFETs. And if we also include this inverter, from which we obtain this B bar, so there are total 4 MOSFETs, right? However, in static CMOS logic implementation, we'll require at least 8 MOSFETs. So 4 as compared to 8, you can understand the level of complexity reduction, right? However, nothing comes for free. Pass transistor comes with their own problems. So let us see what are the problems with pass transistor or the issues with pass transistor. First of all, we are talking about N MOSFET, right? And we know for a fact that N MOSFET doesn't pull up any logic level well. So N MOSFET is not an efficient pull-up, doesn't pass a perfect one. So even if the input is VDD, it will pass only VDD minus VT, right? So let's take this simple pass transistor. If its gate is connected to V supply, right? And if its drain is also connected to V supply, what we get here is V supply minus VT, right? It's basically VGS minus or VG minus VT. Why? Because the moment it goes, the moment this voltage goes beyond VG minus VT, effective VGS is less than VT and this transistor doesn't conduct. So the maximum voltage here can be VG minus VT. Whatever voltage you apply to the ground, whatever voltage you apply to the gate terminal minus the threshold voltage, okay? And also, since the body is grounded, the moment you increase the voltage of the source, your body source gets reverse biased and the threshold voltage also increases. So once the threshold voltage increases, this voltage here, it also reduces to V supply minus VT in the presence of this body bias, which is given by this factor, right? So remember one fact, in NMOS transistor, whatever voltage you are giving to its gate terminal, the output will be charged only to that voltage applied at the gate terminal minus VT, okay? And if this is the case, you cannot cascade pass transistor logic by connecting output of first like this to the gate of second. So here what are the inputs of a pass transistor? The inputs are gate terminal as well as source or drain terminal. So if we want to cascade 2 pass transistor gates, we have to apply the output of this gate to input of some other gate, and input can be either the gate terminal or the drain terminal. So what I say here is the pass transistor logic gates cannot be cascaded by connecting output of the first stage to the gate terminal of the second stage. So it cannot be cascaded in that way. You can connect it to the drain, but you cannot connect it to the gate. Why so? Let us see that case. So suppose we are connecting the output of the first stage here, first transistor, to the gate of the second stage. Then what happens if A is 1? So don't see, if A is 1 and if B is 1, what would be node X? If B is equals to 1, B is equals to VDD, what would be node X? It would be the voltage applied on B, that is VDD minus threshold voltage of M1. So this is VDD minus VT N1. Now similarly for this transistor, this pass transistor, if C is equals to 1 and this voltage is VDD minus VT of 1, what would be this voltage? This voltage will be simply VDD minus VT1 minus the threshold voltage of M2. So whatever you see at Y is not VDD or not VDD minus VT of M2. It's actually VDD minus VTN minus VTN1 minus VTN2. So if consecutively you have reduced your voltage over here, it can so happen that it is less than the VM of this and the output is erroneous, right? It can be detected as a logic level 0 as well upon subsequent cascading in a network of logic gates. So this is something which is problematic, and always remember that the voltage here is when A is equals to 1, the voltage here is V applied to the gate minus VT of this transistor. Always remember this. However, if you connect them, like if you connect the output of this to the drain of the second stage, then what you have, this voltage is VDD minus VTN. And now what is this voltage? This voltage is VDD minus VTN2. I mean, if we assume that VTN1 is equals to VTN2, then this is actually VDD minus VTN. So there's only one threshold voltage drop here. However, here the number of threshold voltage drops is equal to the number of stages that you connect like this. Okay, so you should not connect or you should not cascade the pass transistor logic by connecting output of the first stage to the gate input of the second stage. That is the message. Also, output node is high impedance when output is 1. Why? Because the moment this value reaches VDD minus VT, what happens? I mean, the moment the moment this voltage reaches VDD minus VT, this transistor turns off. So once this turns off, it's just floating, right? It's just floating and charged to V supply minus VT. It's not connected to either supply or ground. So that is in high impedance. And also if you, kind of do this as an exercise, if you try to, take this input as A, this input as B, and this input as F. Let's say you are talking about F is equals to A dot B itself. Then if you draw its VTC, that is also input pattern dependent, depending upon whether A is going from 0 to 1, with B equals to 1 or B equals to, or both of them going from 0 to 1. So F actually depends on that. And its VTC is also interesting. It's actually linear. So if you, if you're interested, I mean, that's not very important. So I did not discuss about it because it's quite intuitive. But if you're interested, please try to make that VTC once, depending upon different sets of inputs or different combination of inputs. So apart from this, the other problem is that it's not a regenerative gate. It's not a regenerative gate, right? Because signal is VD minus VT, and it's not, again regenerative. So it's not a regenerative gate, and signal always degrades after passing through network. So the signal degrades, it means that, since it's non-regenerative, so the rise time will be large as you, walk through the network. Or even the delay, even the signal will be quite delayed as you walk through the network. The pulses won't be, having steep rise and fall times just because the signal, just because the gate is not regenerative. So because of that, short circuit currents would be introduced, short circuit power dissipation would be introduced. And what can we do to mitigate it? Let us insert CMOS buffers or inverters after, let's say, some stages, so that we can regenerate signals. See, although we can say that, if you're inserting CMOS buffers and inverters, it is increasing the AVI, it is increasing the delay. At the same time, it's reducing the power because now you have regenerated the signals and short circuit power dissipation is reduced significantly, right? So there will be trade-offs always. Also, voltage swing is reduced. So less switching energy. Why voltage swing is reduced? Because it's only V supply minus V, right? So if the swing is reduced, switching energy is also less. I mean, dynamic power dissipation is also less. So there's another class of pass transistor logic which is used, frequently, and it is inspired from the differential DC-DSL logic. So that is called differential pass transistor logic. So here, similar to DC-DSL, what we do is we take both true and complementary inputs and generate both true and complementary outputs. So some of the examples are shown here. So here you see that we can realize AND and NAND together. We can realize OR and NOR together. And also we can realize XOR and XNOR together. Best part about this is, we are realizing them only using 4 transistors for this circuit and 2 inverters for realizing A bar and B bar. So total we require how many? 8 transistors, and we can realize all sorts of logic and its complement as well, right? It's especially useful, when you are designing XOR or adders, because they can be realized using less number of MOSFETs. So let's talk about a CMOS XOR. 8 transistors plus 4 transistors for realizing, inverted form of inputs. So 12. Here it's only 8. And the best part is, you see all the gates look the same. It's only the combination of inputs that's changing. So the same topology for all logic gates. It's a modular design. Even the layouts would look almost the same. And library design for automation for this also becomes very easy, right? However, as I told you, think judiciously or think rationally. Since A and A bar both are there, and also all the inputs have to be present in the complementary form. So number of transistors is large, inputs is large actually. So there's this routing issue, right? And output here is still a weak one, right? Output here is still a weak one, right? Because you are only talking about NMOS. So output here will also be whatever value you apply here minus V, right? So since the output here is weak one, VD minus VT, the full swing is not there, and therefore you have a reduced noise margin. So these are the problems with this differential pass transistor logic.